In this video, we'll learn about factors and multiples in Math 6. Factors and multiples can be used when solving problems, such as determining how many packages to buy or how long to cut pieces of material. Let's begin by exploring multiples. A chocolate bar can be broken off into 12 pieces. Suppose that you buy several chocolate bars. How many pieces of chocolate could you have? If you were to buy one chocolate bar, you'd have 12 pieces. If you were to buy two chocolate bars, you'd have 24 pieces. 3 chocolate bars would get you 36 pieces. 4 bars would be 48 pieces, and 5 bars would be 60 pieces. Multiplying 12 by the whole numbers 1, 2, 3, and so on gives multiples of 12. You can also find the multiples of a number by starting at and counting on by that number. Sometimes problems involve finding the multiples of 2 or more quantities. Let's explore one of these problems. The blue bus company runs a shuttle every 3 minutes. The red bus company runs a shuttle every 5 minutes. Both companies first arrive to drop off and pick up passengers at 8 a.m. When will the two shuttles arrive at the same time? We can use number lines to find the multiples of 3 and 5. The blue shuttle arrives every 3 minutes. Skip counting by threes gives 3, 6, 9, 12, and 15 minutes. The red shuttle arrives every 5 minutes. Skip counting by fives gives 5, 10, and 15 minutes. Leaps of 3 and 5 both land on 15. The two shuttles will arrive together at 15 minutes. We can extend these patterns. They will arrive together again at 30 minutes, and again at 45 and 60 minutes. 15, 30, 45, and 60 are called common multiples of 3 and 5. The first number listed, 15, is the lowest common multiple of 3 and 5. Returning to the question, the shuttles will arrive at the same time at 8:15, 8:30, 8:45, 9 o'clock, and so on. Next, let's explore factors. An arrangement of objects in rows and columns is called an array. This array of chocolate candies has 2 rows and 3 columns. It's described as a 2 by 3 array. Arrays can be very helpful when thinking about multiplication. How many different arrays can you make from 18 objects? These circles can be arranged in one row of 18. This can be expressed as 1 times 18. Rearranging the circles into 2 rows creates a 2 by 9 array. 18 objects can also be arranged in 3 rows and 6 columns. You might have tried 4 rows, but 18 objects cannot be arranged in 4 equal rows. Attempting 5 rows also leaves a remainder. Still, it is possible to make more arrays. Changing the orientation of these 3 arrays creates 3 more. 1 row of 18 becomes 18 rows of 1. A 2 by 9 array becomes a 9 by 2 array. 3 rows and 6 columns become 6 columns and 3 rows. However, rotating the arrays did not introduce new numbers. It only reversed the order in which they are written in each expression. The dimensions shown, 1, 2, 3, 6, 9, and 18, are the numbers that divide 18 without leaving a remainder. These numbers are called factors. A factor rainbow can be helpful to make sure that no factor has been missed. Notice that factors come in pairs. Like we did with multiples, we can solve problems that involve finding factors of 2 or more quantities. Two ribbons, blue and yellow, measure 30 and 20 centimeters long, respectively. The two ribbons must be cut into smaller pieces of equal length. For example, each ribbon could be cut into 1 centimeter pieces. Or each ribbon could be cut into 2 centimeter pieces. What is the largest cut that could be made? Since 5 is a factor of both 30 and 20, each ribbon could be cut into 5 centimeter pieces without leaving a remainder. 10 is also a factor of both 30 and 20. Each ribbon could be cut instead into 10 centimeter pieces. The largest cut that could be made is 10 centimeters. 1, 2, 5, and 10 are called common factors of 20 and 30. The largest of these, 10, is called the greatest common factor. Next, we'll apply our understanding of factors and multiples. How many chocolate candies do you see? Use mathematical language to describe how you see them. You might have seen 6 groups of 6. We can say that 6 is a factor of 36. Or 36 is a multiple of 6. Or you might have seen 3 groups of 12. We can say 3 multiples of 12 make 36. Or you might have imagined them rearranged in rows and columns. A 4 by 9 array shows that 4 and 9 are factors of 12. Let's take a closer look at lowest common multiples versus greatest common factors. What is the lowest common multiple of 7 and 21? The multiples of 7 are 7, 14, 21, 28, 35, 42, and so on. The multiples of 21 are 21, 42, 63, 84, and so on. Notice that 21 appears in each list. So too does 42. In fact, every third multiple of 7 is a multiple of 21. The lowest multiple common to both 7 and 21 is 21 itself. What about the greatest common factor? What is the greatest common factor of 7 and 21? The factors of 7 are 1 and 7. The factors of 21 are 1, 21, 3, and 7. 7 and 21 have factors of 1 and 7 in common. 7 is the greatest of these common factors. The GCF of 7 and 21 is 7. Let's turn to applying lowest common multiples and greatest common factors in contextualized situations. Hamburger patties are sold in packages of 6. Hamburger buns are sold in packages of 8. Suppose you plan to host a party for about 70 people. You do not want any patties or buns left over. How many packages of each should you buy? We can use a 100 chart to help solve the problem. The number of patties can be represented by placing red chips on every 6th number. The number of buns can be represented by placing blue chips on every 8th number. The numbers under the red chips list multiples of 6. The blue chips cover multiples of 8. Notice that 24, now purple, is a common multiple. It appears in both lists. We can continue to place red and blue chips on multiples of 6 and 8 respectively. Once more, purple indicates common multiples, 48, 72, and 96. Since the party is for about 70 people, you should buy 72 patties and buns. There are 12 groups of 6 and 9 groups of 8 in 72. You should buy 12 packages of patties and 9 packages of buns. Let's solve another problem. Suppose that you manage a hockey league. 72 players sign up. 30 skaters play defense and 42 play forward. Each team must have the same number of skaters who play defense and the same number of skaters who play forward. What's the greatest number of teams that can be made? The factors of 30 and 42 are listed here and here. The greatest common factor is 6. 30 defenders and 42 forwards can be split into, at most, 6 teams. The greatest number of teams that you can make is 6. Closely related to factors and multiples is the concept of prime and composite numbers. This will be the focus of the remainder of this video. Let's revisit the 2x3 array of chocolate candies from earlier. What if we added one more? How many different ways can you arrange 7 chocolate candies? Seven objects can be arranged in one row of 7 or 7 rows of 1. 7 has only 2 factors, 1 and itself. Such a number is called a prime number. In contrast, 6 has more than 2 factors. Its factors are 1, 2, 3, and 6. A number with more than 2 factors is called a composite number. Which numbers are prime? Which numbers are composite? Next, we'll explore a method for identifying prime and composite numbers. We begin with a 100 chart. 1 has only one factor, 1 itself. It is neither prime nor composite. 2 has 2 factors, 1 and itself. Hence, 2 is a prime number. Multiples of 2 greater than 2, such as 4, 6, 8, and 10, are composite numbers. In fact, every even number greater than 2 is a composite number. That is, in addition to 1 in itself, the factors of every even number include 2. 3 is prime. Its factors are 1 and 3. We can identify more composite numbers by finding multiples of 3 greater than 3 on the 100 chart. Notice that this includes some of the even numbers that were already identified as composite. For numbers that are multiples of both 3 and 2, I'll revert back to using red. 5 is the next prime. Multiples of 5 greater than 5 are composite. This results in identifying new composite numbers in the 5s column. Composite numbers in the 10s column were pointed out earlier. This process of identifying composite numbers through multiples of a smaller prime is continued using 7 and 11. Notice that each multiple of 11 greater than 11 was determined earlier to be composite. The same holds true for the remaining numbers in white. Multiples of 13, 17, 19, and so on will not generate composite numbers not already identified as multiples of 2, 3, 5, 7, or 11. Therefore, all of the remaining numbers in white are prime. Eliminating the composite numbers from the 100 chart leaves all of the prime numbers up to 100. This ancient algorithm for finding primes is called the sieve of Eratosthenes. Here are the prime numbers less than 100 listed in increasing order. Let's apply our understanding of prime and composite numbers. Express 30 as a product of prime factors. One way to express 30 as the product of 5 and 6. This representation is called a factor tree. Branches of 5 and 6 below are said to be factors of 30 above. However, we were tasked with expressing 30 as the product of prime factors, and 6 is composite. 6, however, can be written as the product of two prime numbers, 2 and 3. This extends one branch of the factor tree. 5 times 6 is equivalent to 5 times 2 times 3. Each of these factors is prime. Can you draw a different factor tree for 30? What do you notice? Whether you start with 30 as 5 times 6, or 3 times 10, or 2 times 5, when factored fully, the prime factors, or bottommost branches of the trees, remain the same. Next, we'll solve one last problem. A number is between 20 and 30. It's a prime number. What could it be? There are 9 numbers between 20 and 30. Of these, 4 are even. Here are factor trees for each. We can also rule out 25, since it's a multiple of 5. 21 and 27 are composite. Each is divisible by 3. 23 and 29 each have 2 factors, 1 and themselves. They are prime. The number could be 23 or 29. This aligns with the list of prime numbers that we found earlier. Next up, curricular connections. This video addresses several learning standards in BC's Math 6 curriculum. In content, we learned about factors and multiples, including greatest common factors and lowest common multiples. Your child may be engaged in several curricular competencies in their classroom. These describe the doing of mathematics. Let's highlight a few that we engaged in this video. Throughout the explorations, we developed understanding of factors and multiples through problem solving. For example, we developed a conceptual understanding of common multiples when we solved a problem involving 2 different bus schedules. Later, we applied this understanding to solve a problem involving different sized packages of patties and buns. Further, we visualized mathematical concepts using arrays, number lines, 100 grids, and factor trees. Finally, we used mathematical language to discuss how objects, like chocolate candies, could be arranged. We hope that you found this video helpful when supporting your child in their mathematics learning. Please check out the other videos in this series.